Good evening to all of you. Today is our week 14, and this is the last week. And today we are going to discuss the linear programming problem. So we are going to discuss this linear programming problem here. We will discuss this linear programming problem in 3 parts. So first of all, just raise your hand if my voice. Just raise your hand if you can hear my voice clearly. Okay, so right. So here there are the 3 methods. As I told you in my face-to-face class, a little bit definition. I told you a linear programming problem. We can define in linear programming problem. There are the 3 points are there. First one is the objective function, and the second one is the constraints, and the third one is the non-negative restrictions. And that linear programming problem we can solve by 3 methods. The first method is called the graphical method, and the another method is called the simplex method, and the third method is called the dual simplex method. That is not in our syllabus. So we will discuss only 2 methods. First one is a graphical method, another one is a simplex method. So I will show you how we can solve this linear programming problem through the graphically or through simplex method. And we observe that we are getting the same results. Either we solve by graphical or we can solve by simplex. We got the same results on both the cases. So before going to start, here they are giving a little bit idea how we can draw a graph. Graphing system of a linear inequalities of 2 variables. If we have 2 variables, how we can draw the graph. So first of all, we will tell you how we can draw the graph. After that, we will discuss what is the linear programming problem. So here he says that graphing a linear inequality, we say that so we see that a linear equation of the variables, this is the equation of the line, ax plus by plus c is equal to 0. This is the equation of the line, and has a solution set. It may be exit graphically a points on a straight line in xy plane. So there is also a simple graphical representation for a linear inequalities of 2 variables. There are the equations of the line ax plus by plus c. There are such type of equations are there. So how we can represent the line. So these are the rules are given how we can draw the line. So as I told you in my face-to-face class, so you will read these points, the same thing as I told you in my face-to-face class. Here they say that when you are going to draw a equation of the line, so if there is a less than sign, you will put it into the equality, and for picking, and after that you will draw a checkbox over there, and you will take a point x and y in here, and after that you will take one point is 0, then check the other point what is the other point, and on the next time you will take point 0 on y-axis, then to test what is the point. So this theory is given here. You can understand when I am telling you, so you can understand how we can draw this graph. So here it is given that, for example, this is a equation of the line. It is given there, and you want to draw the graph of this line. So here, first of all, we will replace the less than or greater than equal to sign into the equality sign. So we can write the equation 2x plus 3y is equal to 6. So how we can draw this line? First of all, we will draw a checkbox over there, and in this checkbox we will write x and y and after that, first of all we will put x is equal to 0 in equation number 1. For example, this is equation number 1. If we put x is equal to 0 in equation number 1, what is the value of y? The value of y will be 2. Yes, you are right. Similarly, if we put y is equal to 0 in equation number 1, so we get the value of x will be is equal to the value of x is equal to the value of x will be is equal to 3. Naman, you are right. So we put these 2 points, we got it, and these 2 points we got it. So we combine these 2 points and draw the graph of this line equation number 1. So this is the equation number 1, line number 1. So similarly, the next thing is where is the feasible region? So feasible region means we will put x is equal to 0, y is equal to 0 in equation number 1. If and just check that, if we put it is equal to 0, then it will be is equal to 0 is greater than is equal to 6. So whether this statement is true or false. If this statement is true, then the feasible region goes towards the origin, means it will go towards the origin. If the statement is false, then the feasible region goes outwards the origin. So here our statement is false, it means the feasible region goes outside the origin, yani outward the origin. So that's why the feasible region goes outside. So in my face-to-face class, I gave you the example, the feasible region goes towards the origin. Here it is the example, the feasible region goes outward the origin. So hopefully you understand the concept, what is a feasible region. So next, these are written here. Everything. So the they are giving some other examples for equation. This line you have to draw the line. You will draw the line, and you will write the feasible region here. So again you will write these things. There are 2 equations and 2 unknowns. If you draw the line of these 2 equations, so we will draw how we can draw the lines. So first of all, for line number 1, we will draw this line and draw the feasible region. It is going outward the feasible region. And similarly for the line number 2, this is line number 2, we will draw the equation of the line, and the feasible region of the line number 2 goes upward. And what is the common section between these 2 lines? The common section between 2 lines this is the common section between 2 lines. So we say that this is the feasible region between 2 lines. So the points are, this is 1 point, this is the point P, and this is the other side. So this is called the feasible region. In this way we will say that it is called we can solve any problem with graphically. So it is a simple type problem. So now the other definitions are: the solution set of a system of linear equation is bounded if it can be enclosed by a circle, otherwise it is bounded. So any problem, if it is enclosed in a circle, then we say that it is bounded. I will show you from a example. I will show you what is bounded or unbounded. So the solution of a problem we just discussed is unbounded. Unbounded means, since the solution cannot be enclosed in a circle, means we cannot enclosed in a circle. So if we draw the circle, so we cannot enclosed in a circle. So it is unbounded because of this region is going outside. So we cannot, it is going up to infinity. So we cannot enclosed in a circle. So we say that it is unbounded. If the problem is enclosed in a circle, for example, we have a problem like this, and it can if, for example, this is the problem, this is the feasible region, this is the feasible region. So this is the feasible region, and you know this feasible region can be enclosed in a circle. So we say that it is bounded because of this feasible region is enclosed in a circle. It is bounded, and this cannot be enclosed in a circle, so it is unbounded. So maybe this type of one line objective questions maybe appear that which one is the bounded and which one is unbounded. You will say that when a feasible region enclosed in a circle, then it will be bounded. So for example, this is a graph of the two equations. There are the two equations are given, equation number 1 and the equation number 2, and we draw the graph of these two equations. So we found that this type of graph we can represent, and there are the and we draw the feasible region. So with the feasible region, this is the feasible region, this is all the feasible region. So tell me whether it is this feasible region is bounded or unbounded. So whether this feasible region is bounded or unbounded. Yes, any comments about it? The feasible region is, what you say? Any comment? This feasible region is bounded or unbounded? So just check it whether this feasible region can be enclosed in a circle or not. So your answer is yes, it can be enclosed in a circle. So if it can be enclosed in a circle, so you can say that it is bounded or unbounded. It can be enclosed in a circle. So it is, yes, it can be enclosed in a circle, so it is bounded. Note that the solution to this problem is bounded since it can be enclosed by a circle. So we can say that it is a bounded. So hopefully you understand what is the bounded and unbounded. Any question up to here? So can we proceed further? So can we proceed further? Anyone is present or not? I hope you are. Nobody is present. All of you are going. Okay. So if you okay, it's all right. Dear no one, you are present. So I'm asking the question that. So this is called the bounded. When a solution is enclosed in a circle, then we say that it is bounded. Otherwise, it is called unbounded. So now let's we proceed. So let's we proceed to linear programming problem. So linear programming, till now we discussed there are two lines and we can solve these two lines, and till now we discussed there are the equation of the two lines, and we can solve these two lines, and we got there is a feasible region. Till now we did here up to here, but now there is a linear programming problem. Here in linear programming problem, we have the two lines as usual. The equation of the two lines are same. There is no any change, but there is one thing extra is there. There are two things extra is there. One thing is there is an objective function is there. This is called a for this is an objective function, yani maximize or minimize what we want to do. And the second thing is there are the non-negative restrictions are there. So these things are extra from the others. So now I will show you how we can solve this type of linear programming problem. So as I told you in my face-to-face class, the two ways, one way is graphical, the other way is simplex method. So first of all we will discuss the graphical method. After that we will discuss the simplex method. So there is a definition of the linear programming problems is there, and there are some problems is given. There are some examples are given. So you will read these examples, and there is a data of the example is given, and the finally example is this. This is the example. In short, we want to maximize the objective function this subject to the system of inequality this, and we will discuss the solution of this problem this. So we want to, this is the problem number one, this is the example number one. Now similarly there is a second example we will discuss. There is a example number two, and there is again the data of the example is given there. The data of the example is given there. So this is example number two. The example number two is we will comprises, this is the example to minimize the objective function. So we have to minimize this, yani this is minimize. So minimize the objective function subject to these three constraints are there. There are three constraints are there, and subject to non-negative restrictions. So there are two examples. We discuss example number one and example number two. Example number one is for the maximize the objective function. Example number two is to minimize the objective function. So let us we solve one by one these two problems by graphical method and by simplex method. So now let us we start example number one, maximize the objective function by graphical method. So here we will start the graphical solution of the linear programming problem. So I will share my desktop for better understanding for the PowerPoint slides. The presentation is good. I will share my desktop so that you can understand clearly. So this is the graphical solution of the linear programming problem that we are going to discuss. So there are two problems. Example number one is for maximizing, and example number two for the minimizing. Let's see how we can solve. So first of all, we will write the physical solution of the set of optimal solution. There are the theories are written here. You will read these theories. I will tell you directly from the example. I will explain you what's going on. So this is the problem, example number one. Maximize the objective function p is equal to x plus 1.2y, and subject to the inequality 2x plus y is less than 180, x plus 3y is less than 300. and x is greater than 0 and y is greater than 0. So we will solve by graphically. We first graph the feasible set S for the problem. So first of all, we will draw a graphical solution for the inequality 2x plus y is less than 180. Consider the positive points x and y. So we will first of all we will put x is equal to 0, then we will get y is equal to 180. Second time we will put y is equal to 0, so we get 90. So we draw these 2 points on a graph. The first point is here, the other point is here. What about the feasible region? If we put x is equal to 0, y is equal to 0, so 0 is less than is equal to 180. So this statement is true or false. So you say that yes, this statement is true. So the feasible region goes towards the origin. So we can say that the feasible region goes towards the origin. Now similarly, for the second line, we will draw again for the second line x plus 3y is less than 300. So we draw the checkbox and draw the 2 lines, 2 points, and these 2 points are 0, 100 and 300, 0. After that we will check whether if we put x is equal to 0, y is equal to 0, so we check either 0 is less than is equal to 300, so our statement is true. So it means the feasible region goes towards the origin. So we draw the feasible region. The feasible region goes towards the origin. Now in the next we will take the common feasible region. Whatever the common feasible region between the 2 lines, the common feasible region is this. So we know the coordinates of each corner point except the final P point, except the cross section point. So we will find the cross section point by simplifying both these 2 equations. So when we simplify, these are the coordinates we can find, and the C coordinates we can find after solving the line number 1 and 2. So when we solve these coordinates, we will find that we will put the value of these corner points in an objective function, that is a0, 0, and x is equal to 0, y is equal to 0. So we got P is equal to 0. Similarly, at point B, at point C, at point D, we will found at every corner point we found some different value. Now what is the maximum value here? So you observe that the maximum value here is 148 at the point 48 and 84. This is called the maximization problem. This is called a feasible region, and the coordinates of the feasible region is at C, that is 48 and 84. In this way we can solve it. This is the green way is called the feasible region. So in this way we can solve the problem. Now let us again, we are going to discuss a second number problem, that is minimize the objective function. So this process is the same, there is nothing changed. We do the same process as we did earlier. So there is a objective function and there are the constraints are there. 3 constraints are there, 1 objective function and 3 constraints, and we have to minimize this. Up to here we are always maximize. Here it says that minimize. So what we did, we will draw the graph one by one. So we will draw the graph of the feasible region. We write this is the region that this is the region up to infinity. Now similarly we will draw the graph for the second line. I will give you 1 minute. We will think how we can draw. So here we observe that there is a feasible region goes because of our, if we put x is equal to y is equal to 0 here, so this statement is false. It means the feasible region goes outward from the origin. So similarly for the second line, the second line is, we will draw the second line by drawing the check post, by drawing the box square over here, and put, once we put the value of x is equal to 0 and find the value of y, and in the second time we put y is equal to 0 and then get x is equal to the value of x, we got something. So what about the feasible region? Feasible region goes towards the origin or outwards the origin. What do you think? The feasible region goes towards the origin or outward the origin? So yes, if we put x is equal to 0, y is equal to 0 in equation number this, in this equation, so we found that this is x plus x is 0, and 0 plus 0 is greater than 2100. So this statement is false. So when the statement is false, it means the feasible region goes outward from the origin. So the feasible region goes outward from the origin. Now for the third line, this is, we draw the equation of the third line. So this is the third line, and once we draw a drop check box, and after that we put x is equal to 0, we obtain the value of y. After that we put the value of x is equal to 0 and put the value of y. Similarly, we got the 2 points 0, 100 and 300, 0. And what about the optimal feasible region? It is go towards the origin or outside the origin. So when you put x is equal to 0, y is equal to 0 in equation number 1, we observe that the feasible region goes outside the origin. Now combining all these three lines. So when we are going to combine all these three lines, we observe that this is the common feasible region between these three lines. So what are the points are there? The points are these. This is the point A, B, C, and D. There are the 4 points are there, A, B, C, D. So these are the 4 points A, B, C, D. So now the question is maximize. So we will draw the table and check which one have a maximum value. So we will at each position we will put the value in the objective function and check whether it is the maximum value or not. So let us we draw a table and put all these 4 points in a table, and this is the objective function. C is equal to 6x plus 8y. So for the first point 0 to 40, the objective function will be 1920. For the second, B, C, and D. For the fourth point, this is 1800. So tell me which one is the maximum value. So we observe that the maximum value will be at 11. Which one is sorry, minimize. We have to minimize. The problem is minimize the vertex. If we ask the question which one is the maximum value, so the maximum value is 1920, but the problem is minimized, so the minimum value is B 120. This is the minimum value of this problem. So in this way we can solve the graphical method. Now let us discuss the second method, that is called a simplex method. I will show you how we can solve the same problem with the simplex method. The objectives are same, the variables are same, but we will solve by different method, and we got the same result. So let us see, we take the example number 1 as I discussed earlier. So again, I will take the example number 1 and 2. Let's see what happens. These are the theory that you will understand this theory by, I will tell you when I explain this, you can understand easily. So this is the problem number 1, example number 1, and we have to maximize it and use this problem, solve this problem by simplex method. So we can, first of all, we will write the problem into the standard maximization problem. So when we write the problem into the standard, so as I told you in my face-to-face class, we will write some slack and surplus variables, that is 0x1, 0x2. We will write this thing. So there are 4 steps are there in this. So step number 1, it says that first of all you will write the equation in the standard form by introducing the slack and surplus variables. So we will write the slacks variables like u and v. In my face-to-face class I take s1, s2. So here, but they take u and v. There is no any problem. Don't be confused. So objective function is this. This is given here. Now after that, this is the problem. That's the whole problem is written in the standard form. After that, step number 2, he says that just draw the line. Just draw the table of this system of linear equation. So we put all the coefficients. The coefficient of x is 2. The coefficient of x1 is 1. So in this way, the coefficient of this x1, x minus x will be minus 1. So we will put all the data in this table, and the right hand side will 180, 300. This is 180 and 300, and just we are going to solve this problem. So this is step number 3. Now step number 4 is, he says that we have to remove the negative sign from the last row. There are 2 negative elements. One is minus 1 and the second one is minus 6.5. So we will remove this element from the last row. So if you remove this element from the last row, there are some laws are there. The laws is, say, you will assume this as a pivotal column. So if it is a pivotal column, minus 6/5 is a pivotal column. So if it is assumed, then we will divide it with the solution, and we will write there is a ratio. So you will find the other one is a pivotal row and the pivotal element. Perform the pivotal operation. So here we will, as I told you, we will convert it into the 0. Yani our pivotal element should be 1 and the above and below should be 0. So this is the pivotal row and this is the pivotal column, and the last one is the pivotal element. 3 is the pivotal element. So we will convert this problem into the, so now we will divide the whole row, pivotal row, by 3, so that it will be is equal to 1. So we will divide the whole row by 3, so that it will be is equal to 1. Now after that, I will apply the operation on row 1 and row 2, so that they will become 0. So what operation I will apply on row 1? So in row 1 I will apply R1 will be equal to R1 minus R2, and R3 will be equal to R3 plus 6/5 R2. So in this way we observe that if we apply these operations, we will observe that the above and the lower of the leading one is 0. So now, is there anything Now check again, is there anything that is related, that is negative in the third row? So we say that yes, there is a negative, only in there is a negative value here. So we have to perform this operation again and again until we got all the positive value. So we apply the same operation again here, and this is the pivotal element. Now we want this pivotal element should be 1. We will multiply it by 5 by 3. So we will multiply this 5 by 3, it will be equal to 1. So with 3 it will be 1. Now our aim is all the rest of the thing will be 0, and in the same column all the things are 0 below the 1. So we apply the operation row and rest of the thing are 0. So now here we observe that everything is positive in the last row. There is nothing negative in the last row. So we say that this is the optimal solution. So we say that in the last row of the table contain no negative numbers, so an optimal solution has been reached because of there is nothing negative in the last row. So what are the x? The value of x is 48. The value of y is 84. The value of p is 148. So this is the end of today's lecture. So if you have any question, then you can ask me. Yes, we the your question, Naman, you have to remove negative from the third row. Yes, we have to remove the negative from the third row. We will remove the negative. If it is not removed, we will repeat the process again and again. So this is called the linear programming problem. So if you have any question, then ask me regarding to the linear programming problem, regarding to the graphical problem and simplex method. So hopefully you understand this is the simplex method. So hopefully you understand all the concepts, and there is no any question from this topic. So okay, let's wait a minute. I'm going to take attendance. Just wait a minute. Okay, so you can go now and have a nice day.
Recording stopped.